Hello, friends. Today we're going to do some more applications of lines, and we're going to mix in what we did in our previous lesson with the area of shapes. So we are going to be graphing several different inequalities on the same axis. So if you grab yourself some colored pencils or highlighters or crayons, whatever you have available, that would be fantastic. If you need to pause and go do that, fine. If you're ready to go, then here we go. In algebra, you learn how to graph linear inequalities. So we're going to do that and warm up with that and use that today in our algebra or in our geometry lesson. We're going to graph the system of equalities where y is greater than or equal to 1 and y is less than 2x plus 1. Both of these lines are in an easy form to graph. For the equation y is greater than or equal to 1, that is a horizontal line through the y value of 1. Because it can be equal to, we will draw a solid line. And because y is greater than 1, we are going to shade above that line. So I like to do my shading in lines that are perpendicular to, the shading lines are perpendicular to the actual line itself. And I'm going to label that y is greater than or equal to 1. Our second line that we're graphing is y is less than 2x plus 1. That means our slope is 2 with a y-intercept at positive 1. So I'm going to do a y-intercept at positive 1, a slope of up 2 over 1, up 2 over 1. And to get myself some nice accurate points, I will also go backwards, down to, knowing that my slope is positive, I know how I can go backwards and still have an accurate line. Since y is not equal to 2x plus 1, but less than only, when I connect my dots, I connect them with a dotted line. Hopefully you remember that from your wonderful algebra days. Lines have arrows and go forever, and then y as less than where that line falls. So my shaded lines go below where that line is. Excuse me. Is the point 2 a solution? It is a solution if it lands in the double shaded region of our graph. So the point 2 is in the double shaded region. So the answer would be yes. Is the point negative 3, 5 a solution? Negative 3, 5 is not in the double shaded region, so it is not part of the solution. The region is the intersection of how many half planes, how many shaded regions. So a half plane comes from the idea that your line that you drew split your graph in half. Half that is shaded and half that is not. That's what they mean by the half planes. So when we did two equations and two shaded regions, it was the intersection of two half planes. Because it was two shaded regions, one that was green and one that I did orange. Okay, so now I want you to graph the inequality y is less than or equal to x plus 3. So our y-intercept is at 3, and our slope is positive 1. And when I connect my points, up 1 over 1, up 1 over 1, you have to remember whether you're supposed to connect them with a solid line or a dotted line. And as we go through this unit more and more, because we're going to be using these lines as the borders of shapes, we're going to be using solid lines almost all the time. But we still need to remember that it could be dotted line if it's not completely equal to, if it cannot be equal to. According to this, we are shading where y is less than x plus 3. So where y is less than would be below the line. So I'm going to shade below the line. That is this entire side of the graph. Now, if you have a highlighter, you can do it with the highlighter. I just happen to have a crayon function. So there we go. Explain how the inequality creates two half planes. Well, it's pretty simple. One half is shaded, one half is not. A plane is a flat surface that extends forever. So half of this flat surface is shaded and half of this flat surface is not shaded. I am going to remember to label my line. Y is less than or equal to x plus 3. Now here's where our colors come into play, because I asked you to grab 3 different colors. On the same set of axes, graph x is less than or equal to 4, and y is greater than or equal to 2. Use a different color for each one of those, please. Graph them both. X is less than or equal to 4 is a vertical line through where x is 4. And if x is less than or equal to 4, that means it's going to be shaded down below the 4 towards those smaller x values. So that's over here. All the stuff on this side. And then y is greater than or equal to 2 would be a horizontal line through a y value of 2. So there's my line, y is greater than or equal to 2. Get my blue crayon. And that's everything up there. So this becomes a giant shaded coloring mess. But we're going to sort out this mess and make sure you see, I'm going to make sure you see what we're supposed to see out of this. So by tracing my lines, I can just make sure that they are above all the shading and coloring stuff. Because what happens here with the 3 different half planes, each one of those lines created a half plane. And where the 3 half planes overlapped, or where those 3 half planes intersected, we get a triangle. That's the overlapping of the 3 shaded half planes. Now we're going to find the area of that resulting shaded region. So our 3 different half planes created an area of the graph in the shape of a triangle. So find the area of the triangle. While I play around with my markers and coloring skills, coloring tools, coloring ability, you should be finding the area. You might be done already. So our area is base times height divided by 2. So it's hard to see, but you can just count the squares. The height is 5. And the base is also 5. So your area is base times height divided by 2. 25 divided by 2 is 12.5. How many half planes created this region? Well, how many lines did we have? Each one of those lines created a half plane. So 3 lines, 3 half planes. 1 from each of the different inequalities. Each inequality creates a half that's shaded and a half that is not. Okay, next, find the area of the region bounded by the intersection of the half planes created by the following inequalities. Moving forward from this, we're going to kind of limit all the coloring and avoid this situation where I basically have a big giant blob of colors. So what we're going to do is more carefully graph each one of our 3 lines and then just figure out the shape. Because moving forward, what's going to happen is we're going to try to find the area of the shaded region that would be created by the 3 half planes. That means what shape is created by our 3 lines. Once we have the shape created by our 3 lines, then we can answer whatever questions there are. So let's graph these. This first equation, based on our point slope form, gives us the point where x is -5, y is +1, and has a slope of 1/3. So -5, 1, and up 1 over 3. Up 1 over 3, up 1 over 3. And there's my line. I want to connect and draw as many points as I can fit on the graph because I don't know where it's going to intersect the other lines. So if I draw all the points that I can fit on the graph, then I can try to hopefully come up with an accurate point or vertex where the lines will cross, which would be a vertex of the shape that we are creating. Y is greater than 1 is going to be a horizontal line right through where Y is equal to 1. So that's a pretty easy one to graph and to draw. Notice how all of these include the equal to. Have a space there. And then our third line, y-intercept is at 5. Slope is down 2 over 3. Down 2 over 3. So what we're seeing here is we're creating a triangle based on the intersection of our 3 lines. If we did the shading, the shaded half planes would all overlap at the inside or on the inside of our triangle. So now is when I can get my pencil out or my crayon or my highlighter or whatever you have available. And now I can shade where all 3 overlap, and that's going to be inside of the triangle. Now the question says, find the area of the region bounded by the intersection. We have a little bit of a problem here. Based on what we graphed in the equations that were given, if we tried to use the method where I form a rectangle or a box around my shape, the issue is going to be that my vertex here at the top is not at a whole number intersection point. So I cannot just easily accurately count the height of the triangle or the lengths of the rectangles or triangles around the outside. So just for this problem, we're going to skip the area formula, but conceptually, we could find the point of intersection between these two, the red and green line. We could find that point of intersection to get an accurate vertex, and we could use our distance formula to find anything that we needed as far as lengths would be concerned. But we're not going to do all that algebra now. That's algebra we can do a different day. Here's what we want to do. Draw the triangular region in the plane given by the triangle with vertices 0, 0, 2, 6, and 4, 2. I have mine drawn. You do not have yours drawn on your paper, so please draw it. And then we are going to write, we're working backwards. We are going to write the inequalities that describe this region. So that means we are going to write the equations of the sides. So draw your triangle. Don't forget to color it in because it is supposed to be inequalities. So we would have a shaded region on the inside of our shape. In this case, the inside of our triangle. And then we're just going to simply write the equation for each 3 sides. So for the bottom, side AC, we need a slope, and then we need any point. And then we can use point slope form, or if we have the y-intercept, we can use slope intercept form, whatever seems to be more convenient. So for side AC, our slope is going to be up 1 over 2, or you can count. It went up 2 over 4. Up 2 over 4 reduces down to up 1 over 2. And then if you used point A, the origin, the y-intercept is at 0. Or if you used point C, we would have y minus 2. Make sure you use the greater than or equal to sign because the shading from line AC or side AC is up. So the y is greater than. Now for side AB, we need the slope. So 1, 2, 3, 4, 5, 6 over 2, up 6 over 2 simplifies to up 3 over 1. Again, we could use the y-intercept of 0 from point A, or we could use the coordinates for point B to write the equation of that side. And then, sorry about this. And then we can write, once we have the slope, we can write the equation using either point B or point C. How many half planes? 3. Why? Because there were 3 sides, 3 equations, 3 half planes. You have to be careful about which direction the shading goes. That's the biggest issue here. For side BC, this is technically below, so you need to make sure that the y side of your equation is less than or equal to the x side of the equation. For side AB, it is also below, so you need to make sure that the y side is less than or equal to the x side of your equation, just like what you did in algebra. Okay, so try example 4, pause the video, try example 4, and then come back and I'll show you the answers. What you're going to do for question 4 is plot the 4 points. You're going to be given a trapezoid, and you are going to write the equation of all 4 sides. So go ahead and do it, and then I'm going to show you the answers. So once you have your trapezoid drawn, we have the top and bottom, which are both horizontal lines. Those are very easy to write the equations of. Just make sure your inequality symbols show that you have to be below the top side, but above the bottom. So your inequality symbols should show that. And the right side of our triangle, we have to shade below the right side of our triangle and also below the left side of our triangle. So make sure you have the inequality symbols to show that. It doesn't matter if you use point slope form or slope intercept form. Point slope form is easier and less work. That is my suggestion. That's what you had to do on the quiz last week. That's what you're going to have to use moving forward. And that is also the end of our lesson. All right. Just a little over 16 minutes. Hope you have a wonderful day, and I'll see you soon. Peace out.